Well, thank you. Good afternoon to anyone. First, I would like to thank the colleagues from the PSMSL for this invitation, but also for the great job they are doing for 80 years. Of course, this includes individuals working in the past for the PSMSL, but also individuals working in national agencies promoting PSMSL and the delivery of tie gauge data. So the outline of my presentation is as follows. First, I will start by briefly reminding the basic characteristic of tie gauge records. Then I will illustrate the importance of vertical line movements in two case studies. I will show how the GPS can provide a solution for vertical line movement monitoring. And in the last part, I will strive to show that most of the spatial variability in the sea level change from tie gauges come from vertical line movements. So this first slide is to remind the basic quantity that is recorded by a tie gauge, whatever the technology, whether it is a tie pole, a mechanical tie gauge, a pressure gauge, an acoustic gauge or a radar gauge. This quantity is a sea level relative to the ground on which the tie gauges are settled and their benchmarks. This is by contrast to satellite altimetry, whose data are expressed in a geocentric reference frame, that is the center of mass of the Earth, around which any satellite is orbiting. So, long tie gauge records will include climate signals due to ocean thermal expansion or land ice melting, as well as vertical line movements. So the first example is taken from Northern Europe in Vasa, which is in Finland, and the colors of the map here shows the radial crustal uplift from a model prediction of glacial isostatic adjustment, and you can see that the predicted uplift is between 8 and 9 millimeter per year, which is in very good agreement with the GPS station that is nearby the tie gauge, and that is showing 0.5 millimeter per year over the last decade. So combining the vertical line movement information with projections from the IPCC, maybe an update of these projections here, but even with the latest update, it will not change much the purpose of this exercise. Then you will have a sea level by the end of the 21st century at the same level as in the end of the 20th century. So, by contrast, in this second illustration, in the north coast of the Gulf of Mexico in US, in Louisiana, the tie gauge at Grand Isle is showing a large rate of sea level change of 9.1 millimeter per year. And this, of course, is causing dramatic impacts on the coastline, which are illustrated here in two maps from NOAA, this from 1932, and the next one from 2011. And here again, most of the sea level change as observed by the tie gauge can be explained by subsidence, which is shown here from our GPS results. So as a matter of fact, there is a wide range of geological processes that can cause instability of the land upon which the benchmarks or the tie gauges are grounded. Here you have an illustration that was shown by Leslie previously from the PSMSL. Generally speaking, there are two approaches. The first one is using model predictions, if they are available and accurate enough, of those geological processes. And the other approach is the observations from space geodesy. So whatever the approach, it is worth to highlight that the issue is challenging. We are searching for rates of sea level change of about 2 millimeters per year, and to be useful in those studies of climate signals due to ocean thermal expansion or land ice melting, the standard errors should be 1 order of magnitude less than these signals, of course. So, measure if one can, indeed. 20 years have passed since the expression of the idea with a review of the candidate geodetic techniques, and the first results obtained using GPS, the GPS technique. So many lessons had to be learned in terms of how to observe in continuous mode instead of in campaign mode, but also many progress had to be done in how the GPS data should be analyzed. And here I would like to highlight two important milestones. The first is that the GPS data should be processed in a global network of stations in order to recalculate the orbits of the satellites, but also in order to realize a stable terrestrial reference frame. These are key issues when aiming at these tiny signals. So this requires cooperation, international cooperation, but also naturally an international infrastructure which is provided by the International GNSS Service, the IGS, since 1994. The second important milestone is that the GPS data should be processed using the same models, the same corrections, all over the entire data span. And this means that anytime there is a significant progress in the analysis strategy, in the models and in the corrections, you have to reprocess the entire data set from the beginning, which requires large computing facilities to get results in a timely fashion. So, how well? Well, this is This is the latest solution from our group at the University of La Rochelle. The map shows the GPS velocities. The red arrows show uplift, and the blue arrows show subsidence. And what is interesting is that the standard error of these GPS velocities is of 0.3 millimeter per year, which is similar with what you can get from 50-year-long tie gauge records. So this is interesting because we may combine both data sets in this case. So how well do this GPS vertical velocity work at tie gauges? So here we have grouped long tie gauge records in 3 different regions. On the top panel from the Northern Europe, which is a region known to be affected by glacial isostatic adjustment. The Northwestern America in the middle panel, which is also affected by tectonics in addition to the glacial isostatic adjustment. And then the third region is in the Gulf of Mexico, which is far from the influence of glacial isostatic adjustment, or at least it's less dominating. In this region, the dominating vertical land movements come from sediment compaction and underground fluid extractions. So, not surprisingly, when you apply predictions from a GIA model, I forgot to mention that within each region you can notice a large scatter even though the sites are close within a region. And this is measured by the standard deviation, which are given here. So what I was going to say is that it's not surprising that the GIA corrections are not performing well in these two regions, whereas it is performing quite well here, since the scatter has reduced. But in these two regions, they are dominated by other sources of vertical land movement, here tectonics, and here sediment compaction and fluid extraction. And what we got from our GPS velocity field, you can see, is a very nice reduction in the scatter of these trends in each of the regions. So now let's move to the last part of this presentation. This figure on the left comes from a study carried out by Bruce Douglas, who analyzed the entire PSMSL dataset, and in this graphic he plotted the acceleration component of relative sea level against the record length. And from this analysis he concluded that tide gauge records should at least be longer than about 50 years. So another interesting thing to note from this plot is that most of the tide gauge records are showing linear trends. There are only very few ones revealing non-linear components. So the reason behind this criteria is that there are interannual to decadal signals that may affect the estimate of the long-term trend in each of the records. And another plot that I find quite interesting is the same as on the left, but for the trend. So the linear trend of these tide gauge records plotted against the record length. And in this case, you don't see any dramatic reduction in the scatter of the trends, whereas here it was quite important. And these records have been corrected for the glacial isostatic adjustment. So this is something that is quite interesting. And what I will strive to show you is that most of this scatter comes from local vertical land movements in a few minutes. So this summer we carried out a review of the PSMSL dataset. We adopted some common criteria, such as a minimum length of the tide gauge records of 50 years, with at least 70% of valid data. We grouped this, the selected tide gauge records into regions according to the correlation coefficients, and we searched for the nearest robust vertical GPS velocity from our GPS solution. With some constraints, we did not cross any sea. For instance, when we had a long tide gauge record on an island, we did not search for the GPS on the continent. And another criteria was that we did not use GPS stations that were too far from the tide gauge location according to the GIA gradient information. So whenever the gradient information between the tide gauge location, the GPS location, was above 0.4 millimeter per year, we removed this pair of tide gauge and GPS records. And last but not least, we imposed that the GPS antenna should be co-located at the tide gauge in active tectonic areas. Or we imposed that there is other GPS stations nearby that can corroborate the vertical land movements that we are observing at several of these GPS data. So in the end, we end up with 76 high-quality tide gauge records that we grouped into 17 regions with one station up to 11 or 12 stations in a region. And then for each region, we constructed a time series using the approach of Yevroyeva and colleagues, this virtual station technique. So here are represented the 13 multi-station regions for which we apply this virtual station technique. On the left side, the tie gauge records were not corrected for any land movement, and on the right side, they were corrected with our GPS solution. And what we observed is that the regional trends, the scatter of the regional trends reduced from 1.4 millimeter per year when no correction was applied, GPS correction, to 0.5 millimeter per year. And at the individual station level, we saw a reduction from 2.2 millimeter per year, which is quite consistent with what the dispersion that you can see here, to 0.6 millimeter per year. I forgot to mention that all the results that I will show are virtually the same using the 4 single station regions or the 13 multi-station regions. So we did also the exercise with GIA corrections to see what was the reduction in the scatter of the regional sea level trends, and these reduced from 1.4 millimeter per year when there is no correction to 0.9 millimeter per year when there is a GIA correction. So the GPS is almost doing 50% better than the GIA. So then we mapped these regional sea level rates, and here it is just shown when you have this regional time series corrected for the GIA. And from these rates of regional sea level change, you cannot see any or detect any coherent spatial pattern. Whereas when you are applying GPS corrections, distinct behavior between the northern and the southern hemisphere could be detected. So this was a very striking result for us. So we investigated the robustness of our vertical velocity field, and in particular, we looked at any bias coming from the origin of the terrestrial reference frame. So we looked at satellite laser ranging data, but also to other GPS solutions. And the conclusion was that any bias coming from this geocenter stability is not higher than 0.3 millimeter per year. So it could not explain this difference, which is almost 1 millimeter per year. And then also we wonder if our set of 76 tie gauge records were representative of the ocean. And for this, we investigated ocean global circulation models, several ones, and we extract from these models over 100 years, for instance, the SODA model, and we extracted the nearest point from this model, and we reproduce, as with the tie gauge observations, the procedure, and we concluded that there is no significant difference that can be explained because of the representativeness of this set of tie gauge records. The difference between comparing the averages from the models and the global average from the tie gauge or the hemispheric area weighted was not more than 20%. So, and last but not least, we were looking for other studies, but I think Phil highlighted the challenge to find other places in the southern hemisphere. So we looked at the literature, and so far as we could find any literature that was complying with our criteria of long records and some geological evidence, at least, that there is no vertical movements. These are plotted here, and they support this hemispheric difference. So then we pursue the virtual station technique by hemisphere in order to see what was the hemispheric sea level curve. And here you find the results. For the northern hemisphere, we found a rate of sea level change of 2 millimeters per year, and for the southern hemisphere, 1.1 millimeter per year. And any of the statistical tests that we did show this is a 95% or more significant level that they are different. We also pursue this virtual station technique up to the end to get a global sea level curve, which is here. And we got, not surprisingly, what Gevelyeva and colleagues found, that is 1.8 millimeter per year plus minus 0.5 millimeter. But we also do other procedures like area weighting the hemisphere, and we find different rates of sea level change. But this is, I would say, natural given this hemispheric pattern. So to conclude this presentation, I would say that vertical land movements are an important source of spatial variability in sea level trends from tide gauge records that may prevent from detecting any climate signals or fingerprints, but they are also very important to understand what is happening at a given coastline, what are the processes for the relative sea level change that are observed along the coastlines. From this review exercise that we did this summer, I think we have a robust observational evidence that there is a differential sea level rise between these hemispheres within the limitations of the datasets, of course. But these limitations are affecting any other study, including global sea level reconstructions like those that Annie was mentioning this morning from Church and colleagues. Well, I think I will stop here, and if there is any